Hello everyone. In this video I'm going to talk about a topic that looks a little bit challenging because it's not experienced before, but it's not that bad actually when we start to think about it as a simple way of combining two functions. You've done many ways of combining functions: addition, subtraction, multiplication, composition, and all that. This is another way of combining two functions to produce a third function. Uh, it is an integral, of course, since it is a topic here in differential equations. It's going to be an integral that kind of expresses the amount of overlap of one function, let's say g, as it's shifted over another function f, which they blend with each other, it blends one function with another. All right, so the result of the convolution, I will write it down, is there is, let's say, f and like asterisk g, and what that notation means is convolution of f of t with g of t. And this is something that's used in many applications, in probability, in statistics, acoustics, signal processing, image processing, engineering, and all that. So before we get into it and work our examples, maybe one example to think about is, let's say you have a function that represents rain, for example, right? The intensity of rainfall over time. And you have let's call that f of t or x. And another function, g of t or g of x, that represents absorption rate of the ground. So what would be the convolution in this case? If we are interested in calculating the total amount that is absorbed by the ground over time during that rainfall, then that will need a convolution, because there is an overlap. There is rain falling and there is ground absorbing, and pretty much the resulting function from this convolution would show how the ground's water content changes over time as the rain kind of happening. So you can kind of summarize this concrete example as helping us understand how the intensity of rainfall and the ground's absorption rate interact to determine the amount of water absorbed by the ground over a given period. So that's a lot of stuff about it to start giving you an ideas to think about it. Of course, there are many animations online that shows these ideas, but a simple way to start is to think that's a way of combining two functions to get a third function, right? Okay, so let's go ahead and give you an example. Let's say consider this IVP, which is y double prime plus y equal some g of t, and let's put here this initial condition. And the other initial condition, let's just make it y of 0 equals 0. So let, of course, the capital, let's say y of s, to be the Laplace transform of the y on s, or the function if it's f. And capital G of s is going to be the Laplace transform of g on s. So if take both sides, if we take Laplace transforms to both sides, which we've done in the past, you're gonna get Laplace transform of y double prime, which gives you s squared times this capital Y of s minus s this capital Y of s of 0 minus this capital Y of 0 there. That's for the Laplace transforms of the second derivative. Then this capital Y of s equal then this g of s, which is Laplace transform of g. And that simplifies to this, which if you solve for this capital Y of s, you should get 1 over s squared plus 1 times this capital G of s, right? So because you have you factor this capital Y of s and you get this. If we examine this thing, if you use the table and you want to switch this, you'll find that this is Laplace transforms of the sine t, and this is Laplace transform, of course, of g of t. So what happens here is when we have this sine of t and g of t, so we would like to have a simple formula. So when we think about y of t, we want to have these two, this kind of make it simple, sine of t and g of t, or to find it in terms of sine of t and g of t. So kind of based on what we see here. But what we know also that we have here a product, right? So we know that the integral of a product is not the product of the integrals, that not like the sum. When you have two integrals, sum and or a sum, you can split it to two, right? We know that property, but for the product that doesn't work. So we need to express, so this is where the need comes in. We need to express kind of, so we need to express y of t as the convolution of the two functions there, sine of t and g of t. Alright, so let's now give you the definition, because to do that, let's just do a definition. So if you have a function of t and g of t be piecewise continuous, and piecewise continuous, I'll just abbreviate it later this way, on this positive interval, then we define the convolution of f of t and g of t, denoted by this notation is going to be this way. So the convolution of f of t with the g of t is this integral from 0 to t, pretty much the first function f of t minus v, and the second one g of v dv. So let's give you a simple example so we know what's going on. So example, just so you know, if I have the convolution of t with t squared, that's not multiplication, we've seen that by definition. So the first function is t, and I need of t minus v, then times the second function, which is t squared, and I need to put v squared in it, dv. Alright, so that's it. After here, we know what we need to do. We can just have tv squared, this distribute, then integrate, and we get this, and v squared times v is v cubed, integrate is v to the 4th over 4, 0 to t, and when you do this, you get that. So the convolution of t with t squared is actually t to the 4th divided by 12, right? So if it's multiplication, it'll be t cubed, but it's not multiplication. And that gives you the idea. So for example, not just to, not to make assumptions. So for example, if somebody says, what is the convolution of 1 with 1? It's not going to be 1, because if you follow the definition, I'll let you think about it and apply it. If you follow the definition, the answer will be t, which is not 1. All right? And also, if you do 1 with f in the convolution, and you still follow that, it's not going to be f. Not like, the identity thing, 1 times f is f. The identity here does not work. However, does not mean this doesn't break or breaks all the rules and properties, and it's going to be difficult to work with. No, in fact, there are a lot of properties that it is using. So let's talk about them here. So however, it does satisfy some other properties, and I'll give them to you here. And of course, maybe we'll take some use space here and say, okay, let a function f of t, let's say g of t, and let's say h of t, be that piecewise continuous on this interval. So if we have convolution of f with g, it's going to be same as the convolution of g with f. Commutative works, distributive works as well. Associative works, if you want to call them that. And there is this also is 0. The convolution of f with 0 is 0. Alright, let's give you a theorem. So these are properties. Maybe we switch color and give you some theorem as well. So let's say same thing, we have f of t, g of t, they are piecewise continuous on this interval 0 to infinity and of exponential order. So same thing and for f and g, and they are of exponential order. We can set, let's say, Laplace transform of S is Laplace transform of f on S, and Laplace transforms of G is this capital G or big G, and we know about the big F there. Alright, so then Laplace transform of this convolution on S is the product of these two transforms. That's a good theorem to know. And let's do a switch for it, which means the inverse. So now you know the inverse of this right hand side on t is going to equal to the convolution. So the inverse of the right hand side on t is going to be this convolution on t. Okay. Alright, so let's do some examples on this, and the goal here is of course to solve let's say IVP using the convolution theorem. So let's say use the convolution theorem to solve let's say this initial value problem, and we give this way initial condition, and g of t of course is piecewise continuous on 0 to infinity and of exponential order. Alright, so we're going to introduce of course this transform for the y on S, and this big G to be the transform of G on S. Alright, so take Laplace transform to both sides. We know the rule for the second derivative there. It's going to be s squared times the big Y minus s times y of 0, which is 1, minus y prime of 0, which is 1. Then this is the big S, and equal to the big G of S there. Alright, so we can factor, we have this y of S here, it's with s squared minus 1, and what we have left is negative s minus 1. Let's take them to the right side, and we're going to get something like this. Pause the video, try it, see the steps, and then resume. So what do we have? We have now the transform to be when you divide by s squared minus 1, you'll have s plus 1 over s minus 1. So as you see, you have s plus 1 instead of doing s divided by s squared minus 1 plus then 1 over s squared minus 1. So these two we keep together, which we can do, and then divide the term of big G of S by S squared minus 1. Right, and the reason why is because this is S plus 1 and S minus 1. That simplifies this first one to be 1 over S plus 1, right? And the other way will cancel S 1 over S minus 1 when we cancel S plus 1 from the top and the bottom. And we know what the inverse transform for that, so that's why we put these two together, we kept them together. So let's skip it, not yet. Let's just talk about this one. So this one is just going to be as it is for now. Alright, so we know that if we want switch, maybe do different color just for switch. So now this is y of t, which is y of t is the inverse Laplace transforms for y of s, right, on t. So y of t now, that means let's do the inverse Laplace transform for the first term, then inverse Laplace transform for this second term here. The first term, it's familiar, it's the exponential of t, but if you look at the table, you see it, and a is 1, so 1t. But here we can see that 1 over s squared minus 1, if you look at the table, so let's talk about it here. So maybe for the table, that's going to be Laplace transform of the hyperbolic sign, right? So that's what we have here. We have exponential of t, and we have two functions, which is f of t, using the theorem we have, and I'll show it to you. It's like we have, the answer is going to be g of t convolution with f of t, convolution of f of t with g of t. So let's show you, let's go back to the theorem, which is here. Right, this one here. So Laplace transform of the transform f and the transform g, they're multiplied. The output is the convolution of f of t with g of t, right? So that's the one I'm using. I'm using to say that if this is, oops, this is not working. F of s and g of s. So the answer is going to be the convolution of f of t with g of t. I know from the table the convolution of f of t, let's continue with this pink here, is the hyperbolic sine of t, and g of t, it is something, right? Alright, so now we have a good idea of what it is. Pretty much almost done. Now we can go to the definition. So let's go back to the definition. Alright, the definition says the convolution is this into So we go now and just call it what it is. So you should pause the video, look at the definition, and try to write it yourself, then see if you get what I'm going to put right now. So the exponential of t first, the integral from 0 to t, the hyperbolic sine of t minus v, g of v dv. That's all. That's the solution. Let's give you another example, maybe where we do evaluation of the integral. Alright, let's do that. There is another example. Let's say we want to use this convolution theorem to find Laplace or the inverse Laplace transform for let's say this 1 over s squared plus 1 squared. We know that this is, of course, is 1 over s squared plus 1 times 1 over s squared plus 1. So if we do the inverse for that, that's going to put us in that form of the convolution as the output. So when you do the inverse Laplace transform, again you have here f and g, right? So you expect some answer to be a convolution of these two functions, right? And if you look at the table, this is just sine of t, right? And this is sine of t. So it is some convolution of sine of t with sine of t. Alright, so now we'll go and apply definition. Alright, so let's do the definition, and it's going to be the integral of 0 to t of sine of t minus v, sine of v dv, we have sine times sine, so you know the trig identities product to sum, that's the one we will use. So this is like sine of a and sine of b, so it's gonna be like half of cosine of a minus b and then minus cosine of a plus b. So when you use that, it'll be t minus v minus v minus cosine of t minus v plus v dv. Alright, so like cosine of a minus b minus cosine of a plus b. It's just a trig identity, right? So we have, let's simplify, then I think we can see something also nice there. T minus 2v minus cosine of t dv. I think we can split them and talk about it first. Let's do that. And of course the half is going to be distributed now. So kind of minus the half cosine t dv. Then you see because this is the v, and this is v. We know how to do this, but let's also make it a little bit more interesting. We know that the cosine is an even function, which means if you switch these two, like as 2v minus t, nothing happens, right? Doesn't matter because the cosine is even. So we can do that, make it easier to work with. And yeah, so we can now do this integral, split them. Notice that this is t and this is v, so that's like a number, right? Cosine of t is just like a number. So all right, so I think we're ready to do this. That's gonna produce 1/2 and sine of 2v minus t from 0 to t, and that's gonna produce at a v cosine of t from 0 to t, and so that's 1/4. Now I'll use t will be 2t minus t minus sine of 0 minus t, which is negative t, and 1/2 t cosine of t minus 0 times 0. Look also here, that's why it's important to know these odd and even properties. So this is cosine negative t. It's an odd function, which means the negative goes outside, and that makes this positive if we want to switch the argument from negative t to t, right? So it's an odd function, and that's sine of t. So that makes it 2 sine of t divided by 4. Alright, so I'll give you kind of running out of space and pages, but it's pretty good. So here, think about it. Now you have 2 sine of t divided by 4, so that's going to make it sine of t divided by 2. Then we have t cosine of t divided by 2, so final answer here is sine of t minus t cosine of t over 2 for this question here. So what's the question? Let's see. There it is. Use the convolution theorem to find Laplace transform for this example. We notice it's a product, so we did the inverse. Once we look at a product of these transforms, we switch it to the convolution, and we look at the table, figure out what we're working with. In this case, it's sine, and that puts us, you have sine times sine, which means a product to some rule can be used, and we just keep going with the regular integration, and that puts us in a nice formula, which is sine of t minus t cosine of t divided by 2. Okay, thank you. And I will put some other videos because there may be other ideas, of course, to talk about. And let's see. Yeah, usually with the convolution there is some other ideas to discuss. And if I remember, but they'll need a little bit more explanation, like the impulse response function. It's sort of the topic. It's also interesting. It sounds also challenging, but it's not bad. It's just straightforward formula and know how to work with the transforms. Thank you.